Okay, hello everyone. The title of the paper I will be presenting today is Configurable Fairness for New Item Recommendation Considering Entry Time of Items. These are my co-authors, and I'm Huizhong from Zhang University in China. My research focuses on recommender systems, and as we know that the recommendation environment is dynamic, with new items continuously entering the system. Due to the data-driven nature of recommender systems, this can lead to unfairness towards those new items. And our motivation comes from the master effect. In recommender systems, items with more interactions get overexposed, which leads to even more user clicks on these items. And this can result in a few items getting most of the exposure, harming the diversity of user experiences. And currently, a lot of research is focused on fixing the popularity bias in recommender systems by promoting items that don't get much interaction. However, we believe that it's crucial to understand why these items aren't getting interactions. We think there are two types of low interaction items. First, there are older items that have been in the system for a while. These might be low-quality items that users don't like, which is why they don't get much exposure. And secondly, there are new items that don't have too much time to be exposed to users. And we think they have great potential to attract a huge user base. So we think we should focus on these new items to address the fairness issues. We believe that by ensuring fairness and giving new items a fair chance to be exposed to users, we can improve their exposure and ensure the long-term sustainability of the recommender systems. First, let's look what we found in our study. We ran some experiments using 4 different recommendation algorithms on the movie lens dataset and visualize the results. In our chart, each dot represents an item, and the horizontal axis shows when the item entered the system, with old items on the left and newer ones on the right. The vertical axis shows how much exposure each item gets. Let's start with the first algorithm, most pop. This one recommends the most popular items to users. As you can see, only a few items get most of the exposure, and the recommendation hit rate is pretty low. This shows us that ensuring fairness is really important. And the second method we tried was random recommendation, which ensures that all items get equal exposure. However, its recommendation performance is very poor, making it an impractical choice. And next, we used the MF method to get recommendation results. Finally, we looked at the optimal results. The optimal results represent the ground truth, meaning that each item, including new items, is accurately recommended to the right users. From these results, we can draw a simple conclusion. First, absolute fairness isn't what we want because they have poor recommendation accuracy. And by comparing the 4 algorithms, when we rank the 4 algorithms by their fairness and recommendation accuracy, we see that improving fairness to some extent can actually boost the performance. And as shown by the optimal results, that's what we want. So the big question we study is that how do we balance recommendation accuracy with new item fairness? Okay, now let me briefly introduce the framework of our work. Let's assume we get a recommender system at time t1. We categorize items into 2 types based on their entry time, including old items and the new items. Then we propose a configurable definition of fairness and a metric to evaluate the fairness towards new items in the systems. Filling a gap, and correspondingly, at stage T1, we introduce a method to enhance fairness. Finally, we hope that this optimization method can significantly improve the effectiveness of the cold start program for brand new items. Okay, let's introduce the fairness evaluation metric for new items firstly. We designed this metric with the following consideration. At first, we believe that only items within the same category are comparable. For example, it doesn't make sense to compare the exposure rates of cores and closes. Therefore, our evaluation is conducted only with the same category. And when evaluating a category like books, we first sort all items by their entry time into the system, with larger IDs representing more recently added items. And next, we consider the item ID and assign weights to different items to measure the exposure imbalance between new and old items. And for each item, we calculate its exposure score by checking if it appears in the user's top K recommendations. If not, its score is 0. Then we consider its position in the ranking. Items here in the ranking receive more exposure. And we assign different weights to items for two main reasons. At first, we think old items may have attracted more users and therefore deserve more exposure. So smaller IDs receive higher weights. And second, new items need a stronger boost in fairness to ensure they can be seen by users more quickly. And so we use a simple diagram to illustrate how this metric works. And when TGF is greater than 0, as shown in Figure 1, it indicates that old items receive more exposure, with a higher value indicating a larger gap between old and the new items. Conversely, when TGF is less than 0, as shown in Figure 3, it indicates that new items receive more exposure. And when TGF equals 0, it indicates that both new and old items get equal exposure, showing a fair system. And next, there's another issue to consider. People's demand for new items varies across different domains. And for example, in e-commerce, people tend to prefer older items because they have built up higher credibility and get more trust from users. On the other hand, in the news domain, people prefer to explore more novel content. Therefore, we need to propose a configurable definition of fairness that can adapt to the specific recommendation domains. So, therefore, based on the degree of fairness, we propose 4 levels corresponding to the 4 situations we mentioned earlier. We believe that strict fairness is not what we need, so we introduce the conditional fairness. It allows for some exposure difference between new and old items. We use a parameter epsilon to control it. And when we want new items to receive more recommendation, we can decrease the value of epsilon. Therefore, our definition can flexibly adapt to different recommendation domains. And on the other hand, for existing algorithm, which we rated as conditional discrimination and strict discrimination, we aim to improve their fairness to reach the second level, conditional fairness. Okay, based on the above definition, we can accurately analyze the fairness level of a recommender system and determine the direction for optimization. So the next question is how to enhance the model's fairness to the desired level, achieving a trade-off between recommendation accuracy and fairness. To address this problem, there are 2 technical challenges that need to be overcome. Firstly, in our defined exposure resource matrix, the key parameter, the ranking position, we cannot get it during the training process. Therefore, an accurate estimation method needs to be proposed. And secondly, how to improve fairness to a specific level is another challenge to be solved. And to solve the first problem, the traditional calculation method for ranking is determined by the pairwise comparison of the predicted score of the items. However, this method is non-differentiable, and some related works use sigmoid function to simulate the ranking. However, this approach have significant drawbacks. So we propose a very simple estimation method, considering we only need the relative rankings of items. So we can use the model's predict score for estimation. So in this way, we can ensure differentiability. And we consider 2 points. First, whether the item's predict score appears in the top K position for users, denoted as 1 if yes, 0 otherwise. And this allows us to focus on optimizing the top K list for users. And second, the predict score is positively correlated with the model's ranking position, so we can use its average for estimation. And to optimize model fairness, we propose a 2-stage training method. Firstly, we pre-train the model using BPL loss to enhance its recommendation performance. And building on this foundation, as mentioned earlier, we introduced the TGF as part of the loss function, focusing on optimizing the top K items for users. The optimization objective is to adjust the model during training to to the site epsilon value, aiming to achieve the specific level of fairness we proposed. And it's important to note that epsilon can be estimated based on historic recommendation patterns and specific to the recommendation domain. To validate our approach, we conducted comprehensive experiments using various data sets and baselines. And we use NDSH, SIGIR, and HR to measure the model's recommendation accuracy. MTGF represents the average value of TGF calculated across all item categories and is used to assess the overall fairness of our system. And the new item coverage, and the new refers to the recommendation coverage for new items. And first, we conducted the initial experiment to demonstrate whether the recommendation system can improve fairness for new items in a warm start scenarios. The table below shows the experimental results across 2 data sets and 3 backbone models. Both values indicate the best performance. And these results demonstrate that in most scenarios, our method achieves the best trade-off between recommendation accuracy and fairness. We also conducted experiments focusing on the code start process. We used ALDI, a code start method based on knowledge distillation, which is pre-trained on brand new items without any interaction records. And we compared the impact of different baseline optimizations on the code start progress. The results similarly demonstrate that in the majority of cases, our proposed method achieves the best trade-off between the accuracy and the fairness. For a detailed analysis of the results, please refer to our paper. And here's a specific case to explain how our method works effectively. The figure below shows the list before optimization. We can see that the recommender system mainly recommends old items, even though the user doesn't actually prefer these movies. However, influenced by their high popularity, the model tends to recommend them to the user. After optimization, the model improves the ranking of new items that the user likes, replacing the old items the user unlike. At the same time, it retains the old items that the user prefers. This achieves the optimal balance between recommendation accuracy and fairness. We also studied the impact of setting different epsilon parameters on recommendation accuracy and fairness across various recommendation scenarios. It can be observed that as epsilon increases, the value of MTGF gradually increases, indicating a large disparity in exposure between new and old items. This validates 2 conclusions mentioned earlier. Overly strict or lax fairness constraints are determined to the model's recommendation accuracy. And in summary, our paper makes this contribution. We provide a new metric and the definition to address the fairness of new items. And we propose a configure method to enhance new item fairness to a desired level. And we explore the trade-off between the fairness of new items and the recommendation accuracy in different domains. Okay, that's all.
Thank you very much. Yeah, go ahead. Thank you. Thank the speaker.